we want to evaluate the given line integral, where we have the line integral of xy integrated along the curve C with respect to arc length. And we're given the curve C is y equals x to the fourth when x is on the closed interval from 1 to 3, so this will be the curve C. We're also told that rho of x comma y equals xy is a density function of a wire given by curve C. So notice how the density function is the integrand function, and therefore we can interpret the line integral, and therefore the line integral is going to give us the mass of the wire. And this is the second interpretation of the meaning of a line integral. In our first example, we looked at how we can interpret the line integral as area bounded by a curve and a surface given by the integrand function. Looking at our notes below, the definition of the line integral is given here as a limit, where we have the limit as n approaches infinity of this sum of f of x sub I comma y sub I times delta s sub I. So if this function here is a density function of a wire, where it gives the density per unit of length, then we multiply it by a small arc length given by delta s. The limit of the sum of these products is going to give us the mass of the wire. To evaluate the line integral, we need to write the function f of x comma y as a function of t using the parameterization of the curve C, and then differential s is equal to the square root of x prime of t squared plus y prime of t squared dt. So let's first parameterize the curve C, where C is given by y equals x to the fourth. So let's let x, or x of t, be equal to just t, and therefore y, or y of t, would be equal to t to the fourth. We'll also need the derivatives. So x prime of t is equal to the derivative of t with respect to t, which is 1, and y prime of t is equal to the derivative of t to the fourth with respect to t would be 4t to the third. And because we let x equal t, we know t is going to be on the closed interval from 1 to 3. Now let's also write the integrand function, which in this case is rho of x comma y as a function of t using x of t and y of t. So rho of x of t comma y of t would be equal to, well, x is equal to t, and y is equal to t to the fourth, so we'd have t to the fifth. This is all the information we need in order to evaluate the line integral. The given line integral is equal to rho of t is going to be t to the fifth, and then we're going to have the square root of x prime of t squared plus y prime of t squared, which should be 1 squared plus 4t to the third squared dt, and limits of integration for t are going to be from 1 to 3. Let's write the square root using a rational exponent. So we'll have the integral from 1 to 3 of t to the fifth times the quantity 1 plus, this is going to be 16t to the sixth raised to the 1/2 power. Now let's go and evaluate this on the next slide. Here we need to perform u substitution, where we'll let u be equal to 1 plus 16t to the sixth, and therefore differential u is equal to, 96t to the fifth dt. We just have t to the fifth dt, so let's divide both sides by 96. So we have 1 over 96 differential u equals t to the fifth dt, which means in terms of u, we can think of all of this as, again, t to the fifth dt is equal to 1/96 du, and all this would just be u to the 1/2. So the antiderivative would be 1 over 96 times u to the 3/2 divided by 3/2, or 1 over 96 times 2/3 times u to the 3/2. So we'd have 1 over 96 times 2/3 times u to the 3/2, where u is really 1 plus 16 t to the sixth. Let's go ahead and simplify here. There's 1, 2, and 2, and 48 2s and 96. 48 times 3 is equal to 144. So we'd have 1 over 144 times, when t is equal to 3, we'd have 1 plus 16 times 3 to the sixth raised to the 3/2, minus when t is 1, we'd have 1 plus 16 times 1 to the third raised to the 3/2. So we have 1 over 144 times this is going to be 11,665 raised to the 3 halves minus, this is going to be 17 to the 3 halves. So this would be the exact value of the line integral. As a decimal approximation, we would have 8,748.6383. And again, in this case, this would be the mass of the wire along the curve C. Now we weren't given the units though, so we don't know if this should be slugs or kilograms, so we'll leave the units off. But going back to the first slide just for a moment, because the integrand function of this line integral is a density function of a wire along the curve C, the line integral does give us the mass of a wire along this curve here. I hope you found this helpful.